when you're going around that circle, so I can go back to the other slide. When you're going around, you're in this position right here. And as you go around, you want to continue doing what you're doing, which is going in this direction. However, the wall is getting in your way. When you go that way, you are running into the wall. The wall does what? Well, you push against the wall pushes against you in a perpendicular manner, which happens to be towards the center of the circle. That's why it must be a circle. Now, because the wall is pushing on you, what does Newton's third law say? Well, Newton's third law says that if you push against the wall pushes against you. If the wall pushes on you, you push against the wall. So you feel like you're getting thrown against the wall. We talked about this before when we talked about cars, right? When the car turns, you are not getting thrown against the door. The door is actually pushing on you and pushing you so that you accelerate at the same rate as the car, so that you move with the car. Otherwise, you would continue to go in a straight line, much as you were before. So it's very important to recognize that this object, these people on this ride, are going in a circle not because some magical force is doing it. It's because the wall is pushing them towards the middle. They want to keep going straight like this. The wall is always pushing them forward towards the center. Sorry, not forward, towards the center. All right? So the wall is exerting a centripetal force, not centrifugal. Okay, the same thing can be seen when you see like a satellite, right? That's why I have this slide here, is we're looking at this satellite going around the Earth. Well, what here is causing the circular motion? Well, there is no magical centrifugal force. What's causing it to go in a circle is just a normal everyday force, just like the wall was a normal everyday force. The satellite, if there was no other forces, would continue to go in a straight line forever and ever. Why is it not going in a straight line? Well, it's not going in a straight line because gravity is pulling it towards the Earth. So as it moves this way, it is falling towards the Earth. But the Earth, because it's curved, is now falling away from the satellite at the same rate. So when it's here, it's now moving in this direction. Again, gravity pulls it this way so that it stays in its orbit all the way around. There is a centripetal force. The centripetal force is just the force causing the circular motion. It is not a new force. There is no new force there. It's the same forces we've always looked at. It's gravity. It's the normal force of the wall, right? Up in this other one, it wasn't a new force. It was just the wall pushing on him, causing him to go in a circle. The centripetal force, you must recognize, is not a new force. I do not allow you to label a force as just the centripetal force. You can put centripetal force, but you must also tell me what the centripetal force is. Okay, if I'm doing this, yes, I can label this as force centripetal. But you will also label it as the force of gravity so that you know what the centripetal force is. I will not allow you to ever just label something as centripetal force, because then we start to have this belief that there are magical centripetal forces that make things go in circles because they want to. Okay? Doesn't happen. There must be a force there. No new forces, only the forces we've talked about up to this point. All right? Now, what I'd like you to do is take a minute and work out this question. The Earth has a radius of 6.4 megameters, that's times 10 to the 6th. Determine the centripetal acceleration experienced by someone on the Earth's surface at the equator. Okay, so I'm going to let you go ahead and work through that. You're remembering that acceleration, remember, equals v squared over r. You know the radius of the Earth. You should be able to find out the speed at which someone is traveling at the equator, right? Because you know how far it is around the Earth, right? The distance is just 2 pi r, so you can get the distance, and you know how long it takes to go all the way around the Earth. So you know the speed going around the Earth, and so you can do the distance over the time, which is your 24 hours, which you need to put into seconds. All right, I'm not going to work it out. I would like for you to work it out, and then check your answer with the answer I'll give you in just a second. All right, well, hopefully you got something around 0.033 meters per second squared. All right, so very small acceleration required to keep you on the surface of the Earth, right? This does have some interesting things. For example, that means that you would weigh less on the equator than you would on the North Pole. On the North Pole, you're not rotating very fast, so there's less acceleration needed to match the acceleration of the Earth. So, I mean, lots of interesting things that could come from that, but we're not going to go into those today. So, on to the next video. I want to talk about the physics of a turning car real quick. So, I've got a car, which is a box, as always, and my car wants to turn. Well, how does it turn? Well, the driver turns the wheel and magically it just goes, right? Well, no, of course not. When the driver turns the wheel, the tires turn, right? So the tires are now facing this way, depending on whether it's four-wheel drive or, well, yeah, just like that. So the wheels turn, okay? And then the wheels push backwards on the earth, all right? Okay, wheels push backwards on the earth pushes forwards on the wheels. As the car turns, there must be some kind of centripetal force. If there is no centripetal force, then the car would not be able to go in a circle. So, what could be this centripetal force? Well, what force causes the car to actually turn? Well, that's right, it's friction. If there was no friction, when the car's wheels turned, it would just go in a straight line. So what that means is that a component of friction must be pointed towards the center of the curve of the car. That's very interesting because that means that friction is actually the thing allowing the car to turn. Now, why is that significant? Well, what would happen in rain or snow? What happens to friction? Well, friction decreases, right? Which means that this acceleration, this force, is more difficult to achieve because there is less friction, there will be less force, and therefore you will not be able to have as tight of a curve. Remember, it's A equals V squared over R, and if your acceleration decreases because you have less force available, less friction because of the snow or rain or whatever it is, if this goes down, then that means that the radius will have to be bigger. If the radius is too small, then it's going to require too large of an acceleration and you'll spin out. All right? Now, how can we adjust for this? What can we do? Well, the cool thing is we can actually do something. We're not completely at a loss. What we can do is we can put the road at an angle. So now I'm going to go to the side view of the car. So now the car is going into the page. Okay, I'm not going to do a box. Here's the wheels. We're seeing the back of the car, and the car is trying to go around this way, right? So the road kind of turns around. You like my three-dimensional drawing there. It gets smaller as it gets farther away. But he's trying to go from, right now he's going into the page, and he's going to turn over to the left so that he's moving to the left there. All right? So if there's not enough friction, one thing that you can do is if you know that it's going to rain a lot, or if you know that it's going to snow a lot, you put your road at a slight angle. How does that help? How does that help? Again, thinking of the circle coming from here all the way around, if you're looking from above, that means that you need more centripetal force towards the middle, usually supplied by friction. In this case, however, if we look at the forces on the car, right, you've got friction. Okay, when the wheels are turned, friction is going to help push it. You know, you've got friction. What else do we have? We've got gravity, which is pulling down, and then we've got the normal force, which is pushing that way. Usually the normal force just goes straight up, but you'll notice that now, because I've angled the road, the road actually pushes my car. It has a slight, or not so slight, depending on how much the road is curved, it has a slight component in the direction of the centripetal acceleration towards the middle of the circle. And that's why a lot of times, especially by high-speed freeways and highways and things, when you exit the ramp and you have the road that's curving, it'll often be at a slant because then the normal force assists with that curve. Okay? So from there, there's just one other thing I want to talk about.